Good morning, good afternoon, good evening, depending on where you are. I would like to welcome everybody to webinar number 17 in the Eijkelkamp North America CPT webinar series. As you can see on the screen, what we're going to talk about is a response to the question, what else? What else can you do with CPT? And we're going to cover applications of the CPT method. I'm the Eijkelkamp North America Technical Advisor for CPT. And once again, I would like to welcome you to this webinar. Okay, what are we going to talk about? When we talk about CPT, the whole process of CPT is summarized here on the screen. You see a cone truck on the right-hand side that is pushing cones or a cone into the ground at this constant speed of 20 millimeters per second or 2 centimeters per second, 0.8 inches per second. Most important thing is that it goes at a constant speed, and at that cone we measure the tip resistance, the red arrow, the sleeve friction, the green arrows, and then the dynamic pore water pressure. Not necessarily the pore water pressure itself, because as the cone moves into the ground, you create a dynamic effect, and the dynamic effect results that you measure the dynamic pore water pressure, and we'll come to that again a little bit later. And that is being done in accordance with, here at least in North America, the ASTM standard, D5778, but it could also be in accordance with the ISO standard. But really, as I've explained in the past, there's really not that much difference between those two standards. And what you then start seeing in the field is you start pushing the cone, and as you push the cone into the ground, you get those parameters that I just mentioned before, and you can also then correlate those parameters to come up with a soil behavior classification that you see identified here in different colors on the right-hand side. Once again, I want to point out to you that you see here the dynamic pore pressure, not necessarily the hydrostatic pore water pressure. It's the dynamic pore water pressure because of the dynamic effects of pushing the cone. And the beauty is that when you come to the job site, start pushing the cone, and you can issue a report in about 25 minutes, because that's how easy CPT is. It's a very standardized process, and because it's so standardized, it's very simple to create a report and issue it. You don't have to first take samples back to the lab and then wait until they get analyzed and a report has been issued. That you basically can issue the report while you're still on the job site, especially when you have internet access. And in the past, as we started these webinars now well over a year ago, we talked more about what CPT is all about, what kind of equipment you need to perform CPT, and obviously we paid quite a bit of attention to the CPT cone itself. What are the details, and what cone would be best for a given situation? In other words, what cone works best for you? We also talked about the friends of the cone, the modules that you can put behind the cone and that you can push into the soil at the same time to get more information for the same price if you wish. And we'll talk more about those friends and those modules a little bit later in this presentation. We then talked about pore pressure measurements. What it is that you're measuring, it's not the stagnant, it's not the hydrostatic pore water pressure, but it's dynamic pore water pressure. And you can let that excess pressure, the dynamic effect on the pore water pressure, dissipate away throughout using a dissipation test. And then we talked about how to perform CPT in accordance with the standards, what kind of precautions you need to do or take when you perform CPT. And we talked about the reporting part. But then the question came up with quite a few of you was, well, okay, that's fine. And then what? What are you going to do after you've done all this stuff? What happens then? And that was the topic of webinar number 16. And when at that time, we talked about foundation design with CPT data. In a way, it's kind of logical that you use CPT data for that. As you see on the right-hand side of the screen, when you have a pile that goes into the ground, you have an end bearing of that pile, and you have friction along the pile shaft. And together, they carry the load that is on that foundation pile. And when you then think about what we do with CPT, as you see on the left-hand side, we are measuring that end bearing, that tip resistance, as we go down into the ground. So at every single level, we know what kind of tip resistance, what kind of end bearing there is on the cone. And we also measure the shaft friction. And that shaft friction on the cone could give a very good indication what kind of shaft friction you're going to get along the entire pile length. So it only made sense that you're using CPT for foundation design. So then today, now if you started asking what is CPT used for, well, the first thing obviously is providing information on the ground strata, on the soil profile, and to come up with engineering properties, to come up with the information that designers need for foundations of new buildings and structures and all kinds of other things that you want to put on top of the foundation. And a good document to give you some correlations on how to come up with those engineering properties is a document that I mentioned in the past, document issued by Peter Robertson, Guide to Penetration Testing. You can find it on the web as well, but if you cannot find it, just let me know, and I'm more than happy to send you a copy. The question then is, what else? This is the only thing that you can use CPT for. Can you only use it for design of foundations, or are there other applications of the CPT method? And obviously there are quite a few of them, so much or so many really that it's impossible for me to cover everything within the remaining 20 minutes or so of this webinar. So what I want to do is give you some highlights to really show you what is the framework that you can use CPT data for. And really, the first one that I want to mention after providing information to design foundations is something that you see here on the bottom illustrated from a document that was issued in the late 1970s by Schmertman here in the United States. It's a Federal Highway Guidelines to Cone Penetration Testing. And you see on that the title page of the document, they were still using the old mechanical cones with the gauges at the top to read the tip resistance as well as the sleeve friction. But what it was used for, one of the use, at least what was described as one of the options to use it for, is a quality control check on earthworks. For instance, on compaction testing, on embankments, levees, or earth dams. And what you see, the graph on the right-hand side, is basically how that cone resistance has increased if you are using a vibroflood dynamic compaction. On the horizontal axis is the distance away from where you do that. And you see that if you take the fine clay sand, and you start out with a cone resistance of about 500 pounds per square inch. And then as you get closer to where you applied the vibroflood, you can go up to about 2,000. So you create quite a bit of compaction, and therefore you can use it as a quality control system, but you can also see the impact of what you're doing using the CPT count. Another example of that, in a slightly different way, was a project that we were involved with back in 2016 with another part of the organization that I'm working with, and a project in Holland where a open pipe pile was vibrated into the ground. And you can see here how long that pile was, about 27 meters. So about, 90 feet or something like that. And what you had there as well was a diameter of about 4 meters, so about 13 feet or something like that. And the beauty was, after that pile was put in the ground, a CPT was done. That was then compared with the CPT beforehand. What you see here on the left-hand side was the CPT results beforehand, and the blue line shows you the tip resistance, and the red line is kind of an average of that over depth. But you see here a big variation of the tip resistance as you go down. And on the right-hand side, you have the same CPT a number of months after the pile was put in the ground. But what you see now is that the tip resistance basically is very stable, but also much higher. And it basically means that what you did with this pile, you basically compacted the soil pretty much to this level. This blue line indicates to the bottom of the pile, and below that, obviously, there was no compaction, but above that, there was quite a bit of compaction. So CPT is a great way of really performing quality control or establishing what the impact was of compaction. Third element that I want to mention are Geo Hazard Studies. If you want to find natural cavities, obviously in a cavity there is no tip resistance. So that's another way. But you can also determine man-made features. Earlier we talked about the magnetometer module, where you can identify at the bottom of a sheet pile. You can find out whether you have ordnances, unexploded ordnances, buried somewhere with the magnetometer. All kinds of ways of finding stuff that we put into the soil, but also, obviously, like I said, natural cavities that you could determine as because there's no tip resistance. Fourth item that I want to mention are hydrogeological applications, where you try to get more information about that hydraulic behavior and predict the potential impact. And I want to illustrate that with something that I found described in a paper that you see on the right-hand side, where basically you have a tailings pond, and the tailings pond, you have a dam around it, a levee around it, and obviously inside the tailings pond, the liquid level is here at this level, and then slowly it goes down. And what you could do is, in order to find out where the liquid level is, you could put the piezometer into the ground to figure out where that is. Here you see also some drain lines to bring the water level down. But you can also start using CPT to figure out what is going on. And that's illustrated here. What we have done is at a location, you put in the CPT, you measure your tip resistance, the Q sub C, the friction ratio indicated, and since the friction ratio is very low, you can see that it's mainly sand there, and then you have this dynamic pore water pressure that you're measuring. And as I mentioned, since it's dynamic, what you can do is you can let the excess pressure dissipate, and if you let it dissipate, then obviously, slowly but surely, it goes back to the hydrostatic pressure. And what you see now is as a function of depth, you see here what the actual pore water pressure is, not the hydrostatic pore water pressure, but the U0. Sorry, not the dynamic pore water pressure, but the hydrostatic pore water pressure, the U0. And it basically just goes either down or in certain cases it goes up, but it clearly shows you what that the pressure is the function of depth. And the interesting part now is that if you would use just a single piezometer, then you would get an indication of that hydrostatic pressure, but you may then think that you get something that is indicated in the dashed blue line. You can also use a range of piezometers, and then you may obviously get a more detailed line. But if you just use your CPT, you get a very clear indication of what the hydrostatic pressure is using the dissipation tests at a different depth. But you can go one step further than that. And that is where this idea of the cone and friends comes into play. What we've done here is we have pushed the cone, tip resistance, your friction ratio, your dynamic pore water pressure, you should see, probably more likely U2, which is right behind the cone tip. And then with the dissipation test at these 6 levels, and you see the results of the dissipation test here at the bottom, we figured out what the hydrostatic pressure was. But then we also did a seismic CPT by putting a seismic module behind the cone, and we came up with both the compression wave as well as the shear wave velocity. First, the compression wave. The beauty of the compression wave is that it gives a very clear indication where you have the water table itself, where the soil becomes fully saturated. And the reason for that is that the compression wave velocity really changes substantially and very drastically and dramatically when you go from a saturation of about 97, 98, 99% to 100%. It suddenly shoots up to 1500 meters per second, what you see here. You go from here and very quickly you go to about 1500 meters per second, and you stay roughly at that level. 1500 meters per second, about 5,000 feet per second. And you stay at that level. So now you know that your saturation line is over here, and above that, yeah, it is not either unsaturated or not fully saturated. At certain places it was probably saturated. There might be some very small zones in there, but it was not fully saturated. But below the saturation line, you now know it is fully saturated. That is what the compression wave can tell you. What the shear wave velocity can tell you is something else. What you see here, we have determined the shear wave velocities that you see here, V sub s, and then we have normalized that to take into account that the shear wave obviously goes up as you get deeper, and to get the normalized value of the shear wave is this line here. And what you can do with that, you can indication of whether you can get whether liquefaction is possible or whether it's unlikely. There are different correlations for that, also described in that book that I just mentioned to you a little bit earlier, that was put together by Peter Robertson. So now suddenly we can also figure out whether this hydraulic effect can cause liquefaction. So that just gives you an idea of what you can do with the cone to do this hydrogeotechnical survey. And finally, you can use the cone for all kinds of geo-environmental investigations. And that is something that we could talk about it at length again, just like we could talk about all the other items at great length. But what you can do is you can characterize the contamination, but also find the extent of that contamination, as long as you are using enough CPT points to collect data. That's, I just want to remind you once again of something that I started talking about in a previous webinar, webinar number 11, where we talked about the cone and the friends. By putting different modules behind that cone, you can come up with all kinds of different parameters, different measurements. To get a little bit better, some more information about it, there's another publication by Peter Robertson and his daughter Kelly Cabal that you see on the right-hand side. Again, you can get it on the internet, but if you cannot find it, let me know. I'm more than happy to send it to you. The first items that I want to identify there have to do with this Geo Environmental Investigations, conductivity or resistivity, and hydraulic profiling. Based on the fact that you see here, as you have a different type of soil, not a soil behavior, but a different soil type, really, that the electrical conductivity really changes quite a bit. In sand, it is an order of magnitude lower than in silt, and clay is again much higher values of that conductivity. And it then means if you start measuring that with a module behind the cone, you get something like on the blue line. And it measures the electrical conductivity, and it gives you an idea of what kind of soils you have. Over here between 10 and 15 meters, most likely it's sand, and you can say here at the top layers, more silty type of soil. There are other modules available that can do hydraulic profiling, where you basically push water into the soil and you find out what it would take to push a certain flow rate into the soil. And there obviously you see a good correlation, because as the particles get smaller, it's harder to push that water into to the soil. So there's this hydraulic profiling and electrical conductivity may give you similar kind of results. The other thing that you can do, obviously, to find out what is happening in the soil is using the video cone. And what I want to show you briefly is a video here that you see on your screen right now. On the right-hand side, you see the cone going to the ground, and you start seeing, getting an indication of what the soil looks like. On the center part, we've taken all those pictures, put them together, and you see the white lines go down to give you an indication where you are. And then to make it easier, you see here on the left-hand side also a correlation with the CPT readings, the tip resistance, and the friction ratio, or the sleeve friction in this case, the blue line, and the black arrow indicates there where you are, so that you get an indication of what's going on. Obviously, you cannot look at this in real time because the cone would normally go down at 2 centimeters per second. But if you look at here, the amount of time that it takes just to go to 1 centimeter, this is when you go to 21, and we're still at 21, and now we're at 22. Well, in that same amount of time, the cone would have already been about 10 centimeters down, so quite a bit faster than what you see here. But with that, obviously, you can again get an indication of what kind of soil, what kind of inclusions you potentially have. You may see tar particles sitting in here. And obviously, when you don't use visible light, but ultraviolet light, you might use the fluorescence to determine whether you get certain contaminations there as well. That's another example of what you can do with your slide there, with your video cone there. And finally, you can also put all kinds of samplers, liquid samplers, vapor samplers, solid samplers, because while normally we don't take a sample with a cone, because one of the beauties of the cone is that you go down, you don't create any samples, you don't bring anything to the surface, so that you don't, in case of contamination, you don't need to be worried about it. We do have options to take liquid, vapor, or solid samplers with the cone system. And again, that's described in this book, or this publication by Peter and Kelly that I mentioned to you before. That is the conclusion when it comes to environmental surveys is what I mentioned to you before as well. Cone and Friends, it's a great partnership, and then make optimum use of that partnership. Optimum use to get more data, data that you can use for all kinds of applications other than just figuring out what the bearing capacity is of the soil for a foundation. There you have it. In a nutshell, 5 major examples of what you can use the CPT cone for, not just only for geotechnical foundation design, but all kinds of other applications. And if you have a particular application where you say, hey, this is what I would like to do, start thinking about what you can do simply by putting the appropriate sensor in a module behind the cone. Because as you're pushing the cone into the ground, you can put all kinds of other instruments into the ground that suddenly, because with the cone you can go much deeper, may give you a very good, a very informative, good information, be very informative on what you can actually, what you have in the soil. Good example of that was the magnetometer that we talked about earlier. Normally it has a range of about 7 feet, of about 2 meters, but by pushing it into the ground, you can get information much greater depth. Obviously then a cylinder with a diameter of about 2 times 7 feet, or 2 times 2 meters, about 4 meters in diameter. With that, we're nearly at the end of the half hour. We have a few questions that have come in. One suggestion was that Ohio DOT has had great success pushing and leave behind piezometers with the CPT cone. Absolutely, piezometers, to push them away with the cone is a great tool. You have that capability, works just fine. Some decrease, some increase. What you see in your dissipation test, if you have certain layers in there, since you're pushing, pulling the water out with the drain lines, you're not always that successful, and that has an impact on what your hydrostatic pressure is. But I will come back to the person who asked that question in more detail to show you that graph again. Can you talk about CPT versus DMT, CPT versus shear wave velocity? There are all kinds of ways of coming up with the shear wave velocity. Whether you push the shear wave or the seismic sensor with a cone or with another device into the ground, you're going to get the same shear wave. What is really the interesting thing here is how you analyze the data. And maybe that is something that is a topic for a next webinar when we talk more about seismic CPT or downhole seismic testing. What you have to make clear is that the wave, the seismic wave, does not travel in a straight line. And therefore, if you assume that it travels in a straight line, where you do it with the results obtained with CPT or DMT, it doesn't make any difference. You need to make sure that you come up with the right path, ray path. The other thing is when you have CPT versus DMT, every method has its advantages. Every method has its limitations. For instance, when you are using CPT, you can use the CPT data to use a correlation with that, and that's described in that first book that I mentioned from Peter Robertson. You can use the CPT, the tip resistance, and the friction ratio to figure out what an estimate would be of the shear wave velocity. But it's not as accurate as measuring it itself. So therefore, CPT and the seismic cone really is an enhancement. It complements each other, so that makes a lot of sense to use them together. With that, unfortunately, I'm running out of time, so the other questions I will answer later on by email. And with that, thank you very much, and I look forward to seeing you next month.